Okay, well, it's fun to address the Electronic Materials Symposium. Quite a number of my former students have been received the Ross Tucker Award. And so I'm going to talk about things that we're still doing. And it's kind of fun to be looking, at the sunset of your career. I still haven't retired. As John said, I offered a number of different possible topics. And so I'm going to speak largely about work that two of my recent students have done. One, in fact, I just signed off on his PhD thesis yesterday. So first, what is LIDAR? So it originated in the form of radar, and back when radar was first invented, it was done like this, the radio detection and ranging. And so that was done by the military in World War II, and it was all microwave. And so when people said, well, you could do better ranging more accurately because the wavelength is a lot shorter for light than it is for RF, that you could apply the more or less there. If you believe in Maxwell, you say you could do the same thing, and because of the wavelength being shorter. So LIDAR originally was like this for light detection and ranging. But once people started looking at facial recognition and things, so imaging, so they said, oh, this is really pretty nice that the eye actually is more appropriate. And so that's the foundations of the name, and it was largely, not too surprisingly, all developed by the military to start with. They had a driving need for that, but then it has just recently just absolutely exploded. And so things in facial recognition at ATMs, at airports, and smartphones, your computer. So it's starting to replace fingerprints. An application that's quite interesting is the guide star, and the incredible images you can see of the distant galaxies and things with Earth-based telescopes are totally a result of application of this technology and what's called a guide star, where they're able to correct for all the nonlinear effects and temperature and the changes in refractive index that occur. So you shoot a laser up there and you look, and so you look at the reflected image, and it isn't this nice little spot like it was when it left your laser. It's some god-awful thing, so they just apply a mathematical correction to turn that into a perfect spot just like it was when it left, and then apply that to all of the images. And so space-based astronomy today is as good or better than what you can get in satellites in the Hubble. And it's resulted in a huge explosion of new observatories, that the largest one from in the early 1950s until about 5 years ago was Palomar. And that was because if you made a bigger mirror, you collected more light, but it was just a limited blurry image. So there was no real gain. But now, because you can do adaptive optics and segmented mirrors and things, and using MEMS and all the kind of things that a lot of us have worked on the last 25 years, there's just a big effort in really exploring much further parts of the universe that are really enabled by a lot of the technology that I will sort of give you some view of. Drones, those things are all over. And so what I'm going to mainly talk about are autonomous vehicles, because that's one of the big pushes right now, and what several of my students have worked on the device technology for. So it's always good if you speak about something that you know a lot about. And so that these are other things, and particularly gesture recognition and virtual and augmented reality. So for students, I always, and I think this is an incredible example of that, a quote by Herb Kromer, is that the principal applications of any sufficiently new and innovative technology have always been and will continue to be applications created by that. And nobody, and when Charlie Towns was still alive, I can remember him telling about he and Shallow going into the AT&T people at Bell Labs wanting to patent the laser. And the people there said, well, you know, this is a really amazing, pretty amazing idea that you guys got, but it has absolutely nothing to do with communications. So, you know, maybe you could just patent it on your own and, you know, do whatever. So they were not quite far-sighted enough. And so almost every one of those applications I showed you have all resulted in really the last 10 or 15 years. And nobody imagined most of those 15 years or more ago. And so this is what an autonomous vehicle looks like. And that one of the main elements is LIDAR for ranging and distance information. And so I copied this. I was giving a similar talk in Taiwan about the 3rd of December, and in the Chronicle on 2 days before, just the day before I was leaving to get on a plane, there's this story about the CHP arresting a Tesla driver on autopilot. And so when they finally got him stopped, he was absolutely unconscious, had about 4 times the alcohol level for DUI, but they managed to, you know, a policeman pulled in front of the car and then just kept slowing down, and the car stopped. So I said, that's just a measure of how incredibly accurate and how well these things work already today, and they're only getting better. So the critical cost for LIDAR is really cost, because if you look at this, you've probably no doubt seen Google, or now they're all Waymo cars with the little guy up there on the top. And the thing is that the car is about $25,000 and the LIDAR system is $75,000. So, you know, not going to be too big of a market for that unless we can do something about the cost of this. And so one of the key issues is, you know, the technologies that are available. And it turns out that wavelength is quite an important consideration. So if you look at a basic time of flight system, there are different ways you can do this, but this is a simple one where you have a laser and it sends out a short pulse, and then that's reflected back and then on to a detector. Now you can use also, instead of just a single laser, you can use an array of lasers, and you can do things some faster, and that's what some of my students are working on, are VCSEL arrays to improve that. But the detector then receives the backscatter. And the last part I'll talk about is single photon detection, because if you can detect a single photon, then you can greatly increase the distance over which you can do the range finding. So those are the 2 things that I'll talk about, are the laser and the detector, because I've spent my career and my students making things. So again, something I'm a lot more familiar with and have helped guide their direction. So this is one of the interesting things in choosing, you know, in the, even a little further into the infrared, not just barely red, is that the reflectivity is not very wavelength dependent in the near IR. And so if you look at different materials, you can see what so you can see glass isn't so good, but you know, the windshield of a car you may not detect, but the rest of the car you'll see. So the key thing is this one, is that clothing, quite surprisingly, I learned this when I was a graduate student, putting black electrical tape over the slit of a spectrometer, and after a few crazy things I didn't understand, discovered black electrical tape was absolutely transparent in the infrared at about 1 micron. And so that means that it, in the visible, even where clothing would be completely absorbing, it still has about 50% reflectivity. And so importantly, and especially if you drive around campus, you would think, how did these kids ever get in here? They were wearing black clothing, no light, no reflective thing. You said, did they have some sort of a death wish? Anyway, the LIDAR in the infrared would certainly pick these crazy people up and save their life. So there's two issues. One is the background solar radiation. And so there's these strong water absorption bands. And so if you compare what's currently being used around 850 or 900 nanometers, that here's what the level of background is. If you go out to 1500, you can see that it's about 4 times lower. So anything scattered off of buildings and things is going to be a factor of 4 lower. But the real issue is eye safety, and that in the ultraviolet, you can't see it, so it can damage the cornea. In the visible, it's fortunate that it's relatively safe, even though you just have a natural blink instinct and then you can turn away from it. So that if something bright hits you, before it can really do any damage, you've saved yourself. But you still have to be careful shining a laser just right into your eye. The near-infrared, where we want to work particularly, is extremely dangerous because you just don't see it. So you can just look straight at a laser and have no idea until it's burned a spot in your retina. But that being said, it's, you know, they always say, don't create something that's idiot-proof because God will always create a better idiot. But, you know, so it's hard for me, you know, if you shine something out like that, there's not a danger because the light that comes back is scattered enough. It doesn't form a 1 or 2 micron spot on your retina. What's dangerous is when you do this. And so, you know, if you're stupid enough to do that, you didn't pass the Darwin test. But anyway, the government regulations want to protect us, people that aren't so intelligent and do crazy things. And so the infrared, if you get out further, they're eye safe because the light is all absorbed by so much of the water and the bulk of the eye. And so, you know, if you've got a 10 or 20 milliwatt, the sun we look at, you know, is 100 milliwatts on a nice day, and you're not blind from that. And so it's not the total power or energy that's absorbed, it's where it gets focused. And so that's what's so dangerous when you have a laser, is it gets focused right down onto the retina on a 1 or 2 micron spot and zap. So the absorption in the bulk of the eye then precludes it reaching the retina and doing any serious damage. And so this is the maximum permissible exposure. And so you can see it's like 1 milliwatt per square centimeter in the visible and the near infrared. But if I get out here to about 1400 nanometers, it's 100 milliwatts. And so that means I can have 100 times greater power emitted in the laser in the longer wavelength region. And so when you combine those two, that you get about a factor of 400 or 500 if you go out to the longer wavelength. So there's people working on both issues, and obviously if you can put a lot more power out in your laser, you can do range finding over a much greater distance. And you can overcome more challenging things with dust or fog or rain and things that you have to deal with also. So this is looking at one of those systems that's on top of the Google cars, and so it has a rotating motor and it's buzzing around inside, and so it's giving you a three-dimensional image. So there's always a question, do I need that, or could I do something a little bit more sophisticated and make a phased array like radars use? And so with multiple antenna, or in this case, multiple emitters in an array like this, that I can get then by changing the phase of the light along the each of the waveguides, that I can get beam steering. And so obviously that, from a cost, and you could imagine that I can, all that we know about integrating semiconductor materials and optics and nanophotonics, we can make structures like this that can really be mass produced, and so we can make a big dent in that $75,000 whirling widget on the top of your car. So the laser sources, the next few slides are on that, and so you could think of using an LED, but the angular definition and the power that you can get out is not suitable. Solid state lasers that we often use, and you diode pump them, but the cost is still quite high. And what's amazing, particularly if you go to vertical cavity surface emitting lasers, there's a VCSEL in every one of your computer mice today, and there are little 4x4 element arrays now in the back of actually it's in the front of your phone for facial recognition. And so they're able to produce these for a few cents a piece. So this is the direction that my students that have done their PhD on this and now have started a company producing these, and I think they're shipping like 4 million little chips a month to Apple. And so that you can get better signal to noise. They're extremely cost effective compared to anything else. And a lot of that has to do with just the yield and testing that you can get, that you can do on wafer testing because it's a laser as grown. And so you can always optically pump it and see if it lasers, or even after electrical contacts, you can bring contacts down and do wafer testing. And so, you know, over the years, we found being able to do that, you can make wafer maps, and you can pretty quickly figure out, you know, if there's some part of your process or the epitaxy, if there's something that is not yielding quite as well, and fix it. On edge emitters, it's not a laser until you've got bits of sand in your Petri dish, that you have to cleave all these things up, and then you have to place them, you know, you can have a pick and place thing that does that, but still you have no record of where this laser that worked really well came from on your wafer compared to this one that didn't work very well. Whereas on wafer testing, you just have a perfect wafer map, and so you can very quickly fine-tune your process and make far better yielding and lower cost lasers. So then the question is, if we want to go to longer wavelength because of the much greater signal to noise ratio that you can get, you can look at using an indium phosphide based Fabry-Perot laser or a DFB, or there have been a considerable amount of effort on indium phosphide-based VCSELs, but the thing that's different about these is they're all wafer, well, like some of them have dielectric mirrors, but that creates some other challenging problems. But this work, a lot of it was done with gallium arsenide, aluminum gallium arsenide mirrors, DBRs, and then you wafer bonded an indium phosphide quantum well region to it, polished off the indium phosphide substrate, then you grew another gallium arsenide AlGas DBR, wafer bonded that, then you had to remove the gallium arsenide substrate. And so you end up with 3 epitaxial growths and wafer bonding. And the other is that indium phosphide is still mostly a 3-inch technology. There is 4-inch available, but an awful lot of it's done on 3-inch. Gallium arsenide is mostly done on 6-inch these days, and you can even get 8-inch. So the whole scale up is already much more developed there. And I've kind of got 2 groups of students. One, they're all doing gallium arsenide-based VCSELs, but one is working on the shorter wavelength, 850 nanometers, and then another group is working on 1500 nanometers. And so a lot of that long wavelength work came certainly out of my group. We were the only ones in the end that continues to grow these what are called dilute nitride materials. From my standpoint, it's great because they seemingly can only be done successfully by MBE, which I've been doing for 45 years. And all of my students, we've had a lot of MBE capability. And a lot of people that worked on this originally for solar cells decided, if you can't do it by MOCVD, we're just not doing it. And so solar junction still makes the highest efficiency triple junction solar cells because they're based on this dilute nitride material for the smaller band gap. And ultimately, that's what led us in the direction of lasers. So if you look, this is the family of materials that those of us that have worked on the 3-5 materials for the last 50 or 60 years knew well that, and to first order, as you increase the lattice constant, that the coupling between the atomic levels was reduced, and so the band splitting and the band gap were lower. And so you can see this general trend, and it just turned out you can't see anything that lattice matches to gallium arsenide out here. So all of the red LEDs and things were based on this family of materials and all of the original lasers. And it had the incredible advantage that gallium and aluminum, you can mix any combination. You always got the same lattice constant. So sometimes when your technology wasn't so good, when we were just learning about this, and in the early days, I did some things with Herb Kromer and trying to figure out measuring the band offsets and things. And so when your materials technology was kind of primitive, this was a fabulous system to work on, but it wouldn't work out here where ultimately people needed for optical communications. And so all of that is done with indium gallium arsenide phosphide. And so there's a delicate balance. If you change the indium to gallium ratio, you also have to change the arsenic to phosphorus ratio to stay on this line. So it just took a lot more sophisticated technology to do that. But when desperate people get desperate enough, they solve the problems, and engineers are pretty good at that, and that's been the history of engineering. So this was where almost all of the compound semiconductor and LED, lasers and LEDs was done until Nakamura's and Akasaki and Amano's early work with gallium nitride. And so that was exciting because it made visible LEDs possible. But knowing all this history of how 3-5 materials behaved, nobody ever thought of putting nitrogen into gallium arsenide because you were sure that it was going to increase the band gap, not decrease it. But it turns out that it does. And I had the good fortune to one of my really talented graduate students doing a postdoc in Japan at Hitachi and working with Kazuhiko Kondo. And they discovered and experimentally demonstrated that if you put nitrogen in, the band gap actually went down. And we were working on quantum dots and trying to get out here, much like what John was talking about. And we just couldn't get it to go out to long enough wavelengths. We couldn't get it to go beyond about 1.2 microns. So Mike starts sending me email and says, Coach, you better look at this nitride stuff. It could lattice match to gallium arsenide. And so you can balance then gallium and indium and nitrogen and arsenic. And so you can get lattice matched materials over a very large wavelength region. So why was that? Why was it so different? And it turns out that Sean at Berkeley, at Lawrence Berkeley Lab, came up with a theory that seems to be the most accepted and best explanation, and that is that nitrogen, because it's very strongly bonded, it's a very localized, the nitrogen, it produces a very localized level rather than kind of mixing with in a long-range ordering that gives you the band gap. So you get a anti-crossing. Mr. Pauly starts rolling around in his grave if you say, well, this is what the picture is, and so you can't have two states with exactly the same energy and momentum, and so you get a anti-bonding and bonding orbitals that cause two separate bands, one going up and one going down. So instead of this band just moving upward, which is what all of us expected before this discovery, you get one going up and one going down. So that means in this region, you have a smaller band gap material. And it turns out that it's rather fortuitous that compared to indium phosphide, where the conduction band offset is smaller than in the valence band, and because of the small effective mass, it's the main reason you can't get really high pumping power out of indium phosphide-based lasers. Otherwise, they'd be used as all the pump lasers for like neodymium and all the solid-state lasers. But it just turns out we can put just enough indium in, you can do it with gallium arsenide, and so the effective well that you get is much deeper, and so either from temperature or pumping it hard, you can keep the carriers much better in the conduction band quantum well than you can with indium phosphide. So, every once in a while you get a little good luck along with what you're trying to do. And so when we started out, the first lasers that we had a threshold current density of about 20,000 amps per square centimeter. So the material was obviously not too good. But over time, when we got some decent lasers, and so this was the first result that Chris Cauldron and Mike Larson had about 1988 or 90. So you can see that as you went out to longer wavelengths, the threshold went up. And so everybody says, yeah, it's just the nitrogen penalty. But then I had another generation of students in Seth Bank and Homan Ewan that you can see got down here to where it was virtually indistinguishable from the shorter wavelength. And so then making good edge emitters, we said, well, let's see, the whole idea was really to make VCSELs. And so you could do this all monolithically because you could grow on a gallium arsenide substrate. You could grow aluminum gallium arsenide DBRs, have a quantum well, and you could use the oxidation of aluminum arsenide to create a aperture that gave you both electron carrier confinement and that improves the threshold, but allowed you to have a little larger area so the heat sinking was better. And so you got both optical and electrical confinement. So those are all just, sort of good luck. It just happens with that material system. But a combination of things that you can do processing, quite sophisticated processing, give you pretty amazing devices. And so this was the first VCSEL that was a monolithic VCSEL, and it was done by Thomas Sarmiento that was operated at room temperature. And so you can see it's at 1530. And and the threshold current was 8 kiloamps per square centimeter, which is pretty good. The key thing was that there was a lot of drop across the mirrors. And so the voltage, instead of being 1 volt, was 6 volts. So that really limited the power that you could get out of this. So then Tomas and Li Zhao, my last student, started working on attacking that problem to see if they could improve that. So those first ones were all done just the standard way with an NdBr on a gallium arsenide substrate, the quantum wells, and then a p-type DBR. But the absorption in p-type at longer wavelength is just sort of intolerable. So we did some work on using undoped DBRs and an inner cavity contact, but that really still led to significant series resistance. So we decided what we're going to do is put a tunnel junction in there. And so we have then 2 N-type DBRs. But the whole thing can be grown, continuously inside the MBE machine. And the only thing is it does take a little longer because you need more DBRs because the contrast difference between them is a bit less than it is at the shorter wavelength. And because the wavelength is now 1.5 microns instead of 850, the thickness of each of these is twice as much. So, but in my view, probably the only viable solution for lasers greater than 1300 nanometers is to use this kind of tunnel junction approach. So the student that I just signed off on his dissertation yesterday made quite impressively a 32 element. It's one thing to have graduate students that can make a single device, and they carefully pick the one that has, usually not too surprisingly, the one that always has the best performance out, and then they publish their results on that. But you can see Lee processed a wafer, and it had several arrays of 32. So you can see element to element, it's pretty close. And the difference here, in looking at it, was largely a uniformity of the growth. And so the cavity was just slightly different wavelength. But you can see that we got in an array operation up to 30 degrees C. And you can see that the spread, and that's why we knew that the epitaxy was a little bit spread, was because it's certainly not as narrow as just the single laser. But it was pretty impressive getting a 32 element array. And here he fabricated a 400 element array, every single one of the elements working, and got a CW operation up and getting 2 watts out of the array. So that's the story. Pushing forward on lasers, it's still an open question whether you want to use the shorter wavelength or the longer wavelength. But at least we could make long wavelength, quite substantial laser arrays. So the detector was started by Kai Zhang, and this actually was largely originally completely his idea. We had been working on this basic technology for solar cells, but he got talking to some, as students do around here. There's literally no barriers for students to wander between different groups and talk to students in other groups. And first thing you know, you've got something new that's cooked up between these students. And so he was talking with Gordon Weinstein, and they were looking at imaging around obstacles. And so they were really wanting single photon detection. And so that if you look at the existing silicon single photon avalanche diodes, and how they operate, that a normal photodiode operates with maybe 2 or 3 or 4 volts reverse bias in this regime. And so you bring a photon in, it creates an electron-hole pair, and the built-in electric field, or the field that you've got, separates them, and you get a current. And if you've got a good detector, you get essentially one collected electron-hole pair per photon. So you have 100% quantum efficiency. Life is never quite that good. But if you operate in further reverse bias, that you can get the photon coming in, and you get into a region where you can get avalanche multiplication occurring, and so that now you can increase the number of electrons per incident photon. So you typically might get a gain of 40 to 100, but usually never more than about 100. But if you operate in this region where you limit the current with a big series resistor, and you do it in a very short pulse, that when that photon comes in, it really creates a huge number of pairs, and so you get a large number of pairs created, and so you can get something that's pretty comparable to a photomultiplier. So you can get a gain of about 10 to the 7th. But you have to have that thing so that it can't be doing that. Where operating here, you can operate continuously, so you can use that in optical communications where you got photons coming in continuously. Here, you're doing it where you just have a single photon coming in, and then there's a time lapse till the next one comes. But in LIDAR, you're shooting out laser pulses, and you got to wait the time of flight because you want to measure when you receive it, and so then it's after that that you send out another pulse. So the existing SPADs at that time were a trade-off between efficiency and jitter. And so you could make a very thin device like this, and you got the carriers collected very quickly because of the built-in field and a very thin region, but the absorption was relatively poor. Here you could have a red enhanced one or a thick one, and so with the thick one you obviously got 100% quantum efficiency, but if you got a carrier generated here, it generated a pulse instantly. If you had one way down here, it took a long time for that electron to diffuse clear up to the junction and give you a measurable current. So you can see that in those existing ones that the efficiency, depending on the trade-off of jitter and quantum efficiency, and so that's plotted here, and so you can see it's pretty much linear on a semi-log plot of the trade-off of quantum efficiency and time jitter. And so we worked on developing one which was, I'll show you the details of which, in which we could get a significantly higher quantum efficiency with low jitter. So we were able to kind of break this train that existed before that. So how did we do that? So what we did, and it came from work we were doing on making thin solar cells, was to create a nanophotonic structure here that trapped the light, so that instead of the light going through, and in the case of conventional silicon, you had a choice: either make it very thick, you finally collected all the carriers, but then you got a lot of jitter. But if you're just talking about the sun for a solar cell, you just made them 300 microns thick and you were done. In the case of detectors, that then if this nanostructuring provided wave guiding for the light coming in. So now you got the dimension, the longer dimension for strong absorption laterally instead of through the thickness. And because the speed of light is still way fast compared to electrons in the material, the photons that create electron-hole pairs in here, say out here toward the edge compared to here, was virtually insignificant. And so that you got a very good, so we did some modeling of that, showing that if you just had light coming in like this, you can see how it drops off through the thickness, and here that it's dispersing laterally. And so that the probability of photon absorption, you can see with horizontal distance then was much greater than with the control SPAD. And so this silicon is pretty amazing material, and there's so much technology that you can take advantage. We in the photonics world are so thankful for all of the things that the silicon guys have done. You know, they've got billions of dollars invested in this, and we're just the tail that on the dog, taking advantage of what what the big animal has done. And so this shows the oxide pattern mask we used, and we just, not knowing full well exactly what the dimension should be, but from simulation decided 700 nanometers. And so we use this well-known etch on the 111 planes, and if you etch it just with the right spacing and the right time, that you get triangular patterns that become pyramids in 2 dimensions. And so this, you can see, it's just truly amazing how well this works. And so the thing that was really great and is particularly important in doing this for imaging is that here's what the reflectance of this pattern looks like. Now, if I look at different angles at 10, 20, 30 degrees, you can see I can find a place here where the reflectance is almost angularly independent, and it's very low. And so you can design a really good anti-reflection coating, and one which you optimize this dip so that if you're looking at light coming back scattered from a laser, and that can be, you know, in your image at different angles, that it's virtually independent of that angle. And so, you know, again, every once in a while you're lucky. We hadn't realized this until we actually did the simulations and said, whoa, this thing is really going to be quite powerful compared to just a conventional photodiode with an anti-reflection coating. And so this just shows the efficiency at 800, and so we made 2 SPADs on the same wafer, literally, one which just was a planar one. So they had exactly all the same dimensions and everything, and one where we did this etching and created the light trapping. And so you can see the significant, you know, 5-fold increase in efficiency, and the efficiency at longer wavelengths was equally impressive. And so that when we measured the jitter, you can see that, again, we were able to get a device with not only much higher quantum efficiency. And so I can see a couple of my former students back there that are at the company that are now making these. It's been kind of amazing the last part of my career here that it seems like I haven't run completely out of ideas. There are 3 startup companies that have sprung up out of the research that the students did during their time here. So some concluding thoughts about this is certainly there's no dominant solution yet. There's still a lot of moving around and guessing which it might be. Certainly, MEMS is being adopted because it's rather than that circular spinning thing, because it's far more sophisticated, far less costly, and much less ugly on the top of your car, and you can easily put it in the front. You would never notice it in the front of your automobile. That it's that OPAs and solid state approaches are complicated, so flash is the major technical challenges for range and photon collection requiring single photon detection. And so there's a key issue still with wavelength that the near term is certainly already going to 850 and 905 because of all the readily available technology for the lasers, and all the detectors can be silicon. At the longer wavelength, you've got to have both long wavelength detectors and lasers. And so there's a lot of choices for the detector because it's not constrained by power. And so you can easily use indium gallium arsenide phosphide on indium phosphide. But for the VCSELs, in order to make them the lasers inexpensive, you might still do with DFBs and edge emitting lasers, but there's a lot of limitations to those. And so, but the key thing is the huge advantage you get. Not very many things can you do suddenly where you have a difference of a factor of 400 in signal to noise. Usually you're squeaking, doing everything you can just to get an improvement of 1.5 or 2. Here, you just get a factor of 4 to 500, but the devices are a lot more challenging. So these are the students that have done this. These are mostly students over the past 15 or so years that really provided all the foundation work. And Lee did the two-dimensional laser VCSEL arrays, and Kai did the SPAD work, and Tomas did the pioneering work on the tunnel junction. And these are the people that supported it. And so I thought for the students I could pass on. I've been doing this for a lot of years. Maybe there's some wisdom in what I have done. And so one is to pick things that are important and above all, do them well. And don't give up. And I like this quote from Edison, that many of life's failures are people who didn't realize how close they were to success when they gave up. And it's easy to see that, you know, when you've been in the lab and, you know, 3 or 4 or 5 or 6 days turn into a couple of weeks, and then a month, and then 2 months, and you think, damn, is this never going to work? So the important thing is to look and see, even though on one hand, most people would say it's a failure, but if it's better than it was a week before, and you say, well, I learned something new, and if I just incorporate that, and that's certainly the case with working on the long wavelength VCSELs. It took a lot of students over 20 years to get to where they were. So with that, I've enjoyed being here, and thank you.